Space is full of whispers we can't quite decipher, strange signals, impossible objects, phenomena that defy every law of physics we've ever written. Picture this: a radio telescope picks up a burst of noise so powerful, so perfectly aligned with the signature we'd expect from an alien transmission, that the scientist reviewing the data scrawls, "Wow," in the margins, and just like that, the wow signal becomes one of history's greatest cosmic riddles. No explanation, no repeat, just silence and questions. Or consider the Fermi Paradox, the unsettling truth that, in a universe teeming with billions of stars, we should have heard something by now. So where is everyone? These aren't just quirks of astronomy. They're cracks in the foundation of everything we think we know. Today, we're diving into 25 of the most baffling anomalies in space-time, events and objects that shouldn't exist, signals that refuse to be decoded, corners of the cosmos where the rules of reality seem to bend. Some are fleeting, like that infamous wow signal. Others loom over us like the Great Attractor, a mysterious gravitational force pulling entire galaxies toward it at impossible speeds. And then there are the voids, regions of space so empty, so devoid of matter, that they challenge our very understanding of how the universe formed. These aren't just puzzles for scientists, they're invitations for all of us to stare into the unknown and wonder what's really out there. What makes these anomalies so thrilling isn't just their strangeness, it's what they reveal about us. Every unexplained flicker of light, every distortion in space-time, forces us to confront how little we truly understand. The cosmos doesn't play by our rules, and that's the most exhilarating part. So whether it's rogue planets hurtling through the darkness or stars that flicker like someone or something is obscuring them, each of these 25 mysteries is a reminder. The universe is far stranger, far more unpredictable than we've ever dared to imagine. And by the end of this journey, you'll see space not as a static void, but as a living, breathing enigma, one that's waiting for us to unravel its secrets. It was an ordinary August night in 1977 when astronomer Jerry Amon sat scanning rows of data from Ohio State University's Big Ear radio telescope until one line of numbers stopped him cold. Amid the static, a vertical column of alphanumeric code leaped off the page, 6 letters and numbers so anomalous that Amon circled them in red pen and scrawled a single, breathless note in the margin: "Wow." The signal was unlike anything ever detected before or since. For exactly 72 seconds, a narrowband radio burst screamed from the constellation Sagittarius at a frequency of 1,420 MHz, a dead quiet channel reserved internationally for cosmic listening, where no natural interference should exist. Then, just as suddenly as it appeared, it vanished. Here's what makes the wow signal so haunting. It matched precisely the profile scientists predicted for an intentional extraterrestrial transmission. No known celestial object, pulsars, quasars, or passing comets emit such a focused, unnatural pulse. Even stranger, the signal's intensity spiked and faded exactly as you'd expect if it originated from a distant, rotating planet, sweeping past Earth like a lighthouse beam. Yet 4 decades of follow-up scans, including advanced SETI campaigns, have found nothing, not a whisper, not a glitch. Theories, they range from the tantalizing to the absurd. Some argue it was a military transmission bouncing off space debris, except no terrestrial technology in 1977 could have produced that signature. Others suggest a rogue comet's hydrogen cloud, though later calculations showed none were nearby. Then there's the unspoken possibility that for 72 seconds we caught the cosmic equivalent of a ringing phone and missed the call. The coordinates point to a sun-like star nearly 200 light-years away, a needle in the galactic haystack. But here's the chilling thought. If it was intelligence, that civilization could have risen and fallen in the centuries it took their signal to reach us. Or worse, what if they're still out there, waiting for a reply we'll never send? the Wow signal endures not just as a mystery, but as a Rorschach test for our place in the universe. Every unexplained blip forces us to ask, are we alone, or is something or someone just out of earshot? If the Wow signal is a whisper from the void, then dark matter is the universe's silent scream, something massive, everywhere, and utterly invisible. Picture a merry-go-round spinning so fast that the children clinging to it should be flung into the air, yet somehow they stay glued in place. That's precisely what galaxies do. Stars on the outer edges whirl around their centers at speeds that defy the laws of gravity, as if some unseen hand is gripping them tight. Without dark matter's hidden bulk, galaxies would fly apart. The math is undeniable. Over 80% of the universe's matter is missing. We can't see it, we can't touch it, but we know it's there, warping the cosmos like a phantom limb. So what exactly is this cosmic glue? The leading suspects sound like something from a physicist's fever dream. WIMP, weakly interacting massive particles, are theoretical heavyweights that barely interact with normal matter, passing through you right now like ghosts through a wall. Then there are actions, hypothetical particles so lightweight they could dance on a neutrino's fingertip. Some theories even suggest dark matter isn't particles at all, but primordial black holes left over from the Big Bang. Yet after decades of hunting, from deep underground labs to particle colliders, we've found nothing. Here's where it gets weirder. Dark matter isn't just holding galaxies together, it's sculpting the universe's very skeleton. Computer simulations show that without its gravitational scaffolding, galaxies would be scattered like dust in the wind. The cosmic web, those vast filaments of galaxies stretching across the void, owes its structure to dark matter's invisible threads. Even stranger, some galaxies seem to lack it entirely, like cosmic rebels defying the rules. Take NGC 1052DF2, a wispy galaxy where stars drift lazily, barely held by gravity. It shouldn't exist, and yet there it is. The hunt for answers has taken scientists to some of the most extreme places on Earth and beyond. In abandoned gold mines, ultra-sensitive detectors wait for the once-in-a-lifetime ping of a WIMP collision. In space, telescopes like Euclid map dark matter's shadowy fingerprints by watching how it bends light from distant galaxies. Every null result, every dead end, forces us to rethink what matter is. Maybe dark matter isn't one thing but many, an entire hidden zoo of particles, or perhaps we've got gravity all wrong and the universe operates by rules we haven't written yet. One thing's certain, dark matter is the universe's ultimate prank. It's the reason you can't trust your eyes, the reminder that reality is far stranger than it seems. And until we crack its code, we're like ants trying to understand a hurricane by feeling the wind. The cosmos is playing hide and seek, and so far it's winning. If dark matter is the universe's invisible scaffolding, then dark energy is the phantom hand tearing it apart at the seams. A force so baffling that even Einstein doubted its existence before calling it his greatest blunder. Here's the cosmic irony. Just as we began to map dark matter's gravitational grip, astronomers in the late 1990s discovered something far more unsettling. The universe isn't just expanding, it's accelerating, galaxies fleeing from each other faster with every passing moment, as if some unseen repellent is stretching the very fabric of space-time. Enter dark energy, the dominant player in our cosmos, making up a staggering 68% of the universe's total energy. Unlike dark matter, which clumps and pulls, dark energy is eerily uniform, a kind of anti-gravity woven into empty space itself. The numbers are mind-bending. Measurements of distant supernova revealed that around 5 billion years ago, the universe's expansion inexplicably shifted gears, overcoming gravity's pull like a car suddenly hitting the gas pedal. The leading explanation, Einstein's abandoned cosmological constant, a mathematical fudge factor he'd inserted into his equations to keep the universe static, later discarded when Hubble proved expansion. Now it's back with a vengeance, the idea that empty space isn't empty at all, but seething with a background energy that generates repulsive gravity. Yet the math breaks down spectacularly. Quantum physics predicts a vacuum energy trillions of times stronger than what we observe. If dark energy were even slightly more potent, galaxies would have been ripped apart before life could form. Alternative theories abound. Some propose dark energy isn't constant but evolves over time, a cosmic field called quintessence, echoing ancient philosophy's fifth element. Others suggest gravity itself behaves differently on vast scales, or that we're seeing echoes of colliding universes in a hidden multiverse, the most unsettling possibility. Dark energy might one day grow strong enough to unravel atoms in a catastrophic Big Rip. For now, telescopes like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are mapping this acceleration in unprecedented detail, tracing how galaxy clusters bend light and how voids between them grow. But every answer deepens the mystery. Dark energy doesn't just defy explanation, it defies intuition. We're left staring at a universe where the greatest force isn't gravity or light, but the relentless push of nothingness itself. And that changes everything. At the edge of our solar system, two tiny emissaries from Earth, Pioneer 10 and Pioneer 11, began drifting off course in a way that shouldn't have been possible. Launched in the early 1970s, these probes were the first human-made objects to venture beyond the asteroid belt, destined to become silent wanderers in the interstellar void. But by the 1980s, something peculiar emerged in their trajectories. An unseen force, roughly 10 billion times weaker than gravity, was tugging at them, slowing their exit from the solar system by about 300 miles per decade. At first, scientists dismissed it as a glitch, a loose bolt venting gas, or a software error. Yet as years turned into decades, the anomaly persisted, defying every conventional explanation. The mystery only deepened when other spacecraft, like Galileo and Ulysses, failed to exhibit the same behavior. This wasn't a universal quirk of deep space travel, it was something uniquely tied to the pioneers. The numbers were undeniable, an unmodeled deceleration of 8.74 times 10 to the negative 10 meters per second squared, a figure so precise yet so baffling it became known simply as the Pioneer anomaly. For 30 years, it haunted physicists, whispering that our understanding of gravity, motion, or even the fabric of space itself might be incomplete. Proposed solutions ranged from the mundane to the revolutionary. One camp argued it was thermal recoil, heat radiating unevenly from the probe's plutonium-powered generators, acting like tiny thrusters pushing them backward. Others suspected fuel leaks or even the faint pressure of sunlight bouncing off the spacecraft's dish antennas. But meticulous reconstructions of the probe's designs revealed a more startling possibility. The heat explanation only accounted for part of the anomaly. The rest that remained a mystery, leaving the door open for radical ideas like modified gravity theories or unseen dark matter interactions in our solar system's outskirts. Then, in 2012, a team of researchers made a breakthrough. By reconstructing decades-old engineering documents and simulating the probe's heat emissions down to the watt, they showed that thermal radiation could indeed explain most, but not all of the drag. The rest might forever linger in the realm of uncertainty, buried in the Pioneer's long silenced data streams. What makes this anomaly so compelling isn't just the lingering questions, it's the humility it forced upon us. Even in our own cosmic backyard, the universe refuses to follow the script, and sometimes it takes a ghostly tug on a decades-old spacecraft to remind us how much we still don't know. The universe is unimaginably vast, 2 trillion galaxies, each with billions of stars, countless planets. Given those numbers, the cosmos should be teeming with life. So where is everybody? This is the Fermi Paradox, named after physicist Enrico Fermi, who famously posed the question over lunch in 1950 with a bluntness that still stings. If advanced civilizations exist, their presence should be obvious. Yet after decades of scanning the skies, we've found nothing but silence, no signals, no megastructures, not even a single bacterial fossil beyond Earth. The contradiction between probability and evidence is staggering, and the possible explanations are either unsettling or downright terrifying. Take the Great Filter hypothesis, a cosmic bottleneck that prevents life from advancing to interstellar scales. Maybe the filter lies in our past. The leap from simple chemistry to self-replicating life could be so improbable that Earth is a freak accident, or perhaps the filter looms ahead. Civilizations might inevitably destroy themselves with climate collapse, nuclear war, or rogue artificial intelligence before they can colonize the stars. The chilling implication: if we don't find any aliens, it might mean every civilization that ever existed hit the same wall, and we're next. Then there's the eerie possibility that we're being intentionally ignored. The zoo theory suggests advanced societies observe us from afar like animals in a wildlife preserve, adhering to a galactic version of the Prime Directive. Or maybe we're simply looking for the wrong things. What if aliens communicate via neutrino beams or quantum entanglement, technologies we can't yet detect? Interstellar distances alone are brutal. A signal from a civilization just 1,000 light-years away would require 1,000 years to reach us. By the time we reply, their culture could be extinct. But the darkest answer might be the simplest: we're alone. Earth could be a 1 in a trillion fluke, a flicker of awareness in an endless void, or worse, we're first. The universe is 13.8 billion years old, but complex life may need precise conditions. The right metals from ancient supernova, stable planetary orbits, the absence of sterilizing gamma-ray bursts. If we're early, the great civilizations of the future might rise long after our sun has burned out. The Fermi Paradox forces us to confront our deepest hopes and fears about existence. Every silent radio dish, every empty exoplanet whispers the same unnerving question: are we special or just tragically unlucky? Until we know, the stars remain both a promise and a mirror, reflecting back what we most want and dread to find. Imagine a cosmic strobe light flashing with the energy of 500 million suns for less time than it takes to blink. That's the essence of a fast radio burst, or FRB, a fleeting, ultra-powerful blast of radio waves from deep space, often lasting just milliseconds. First detected in 2007, these bursts arrive without warning, packing more punch in a fraction of a second than our sun emits in 80 years. And the strangest part, some of them repeat. Take FRB 1211-2, a burst from a galaxy 3 billion light-years away that flickered like a malfunctioning beacon over 20 times since its discovery. Then there's FRB 1809914, the first FRB traced to a specific source, a magnetar, a highly magnetic neutron star spinning so fast it could shred atoms. But here's the catch: while magnetars can explain some bursts, they can't account for all of them. The energy levels, the repetition patterns, the sheer unpredictability, it's like blaming firecrackers for a supernova. Theories spiral from the plausible to the extraordinary. Colliding neutron stars possible, but mergers are rare, and repeating FRBs suggest a source that survives the violence. Black holes evaporating into Hawking radiation, intriguing, but the math doesn't quite fit. Then there's the elephant in the room: could some FRBs be artificial? The idea isn't as fringe as it sounds. A one-time burst could be natural, but repeating signals with precise intervals like FRB 1812, 14's 157-day cycle raise eyebrows. Imagine a civilization using focused radio beams to propel light sail ships across galaxies, or a malfunctioning beacon from a long-dead culture still pulsing into the void. Scientists are racing to decode these cosmic Morse codes. Telescopes like CHIME in Canada scan the skies daily, while projects like Breakthrough analyze FRBs for signs of encoded patterns. Every new detection peels back another layer of mystery. Some bursts arrive with a telltale twist in their radio waves, hinting at passage through intense magnetic fields. Others come with X-ray counterparts, suggesting cataclysmic origins. What makes FRBs so electrifying isn't just their power, it's their defiance. Their cosmic riddles written in a language we're just starting to learn, reminders that the universe specializes in the spectacularly unexplained. Whether natural or otherwise, each burst is a flare in the dark, challenging us to look deeper, listen closer, and wonder what else is out there screaming into the silence. The cosmic microwave background, the faint afterglow of the Big Bang, should be the universe's most democratic feature, a perfectly even tapestry of ancient light stretched across the sky. But in 2005, astronomers staring at data from the Wilkinson Microwave Anisotropy probe noticed something that made their blood run cold. The hot and cold spots in this primordial radiation weren't randomly scattered as expected. Instead, they seemed to align along a bizarrely specific axis, as if the universe itself had a North Star. Dubbed the axis of evil by a shuddering scientist, this eerie pattern defies the very foundation of modern cosmology, the cosmological principle, which states that the universe should look the same in all directions with no special vantage points. At the heart of the controversy is a number so improbable it feels like a cosmic joke. The chance of this alignment occurring randomly, less than 1 in 10,000. The axis points suspiciously toward the ecliptic plane of our solar system, raising the chilling possibility that it's not a feature of the universe at all, but some grotesque artifact of our own measurements. Yet after years of reanalysis, including data from the Planck satellite, the anomaly refused to vanish. If it's real, the implications are earth-shaking. It could mean the universe has a preferred direction, that our corner of space-time is fundamentally different from others, or worse, that we're seeing the fingerprints of a pre-Big Bang structure, a cosmic scar from something beyond our observable horizon. Skeptics have scrambled for explanations. Maybe it's residual contamination from our galaxy's dust, though meticulous filtering rules out most interference. Others suggest systematic errors in how we model the CMB, but no one's found a smoking gun. The most radical theories that the universe is finite and oddly shaped, like a hall of mirrors warping light on colossal scales. Or that we're seeing the gravitational tug of a parallel universe brushing against ours, a multiversal collision frozen in the afterglow of creation. What makes the axis of evil so unnerving isn't just its existence, it's the philosophical vertigo it induces. For centuries, we've clung to the idea that we're not special, that Earth is a speck in an indifferent cosmos. Now, we're forced to confront the possibility that the universe might, after all, have a front row and a back, and we're staring straight down the center aisle. Until we crack this code, the CMB remains both our oldest relic and our greatest riddle, whispering that the universe is far stranger, far less random than we ever dreamed. Somewhere beyond the Milky Way's blinding starlight, hidden behind what astronomers call the zone of avoidance, a region so dense with cosmic dust and gas that telescopes can barely see through it, lurks the universe's greatest tug-of-war champion. Meet the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxies, including our own, toward it at a staggering 14 million miles per hour. For decades, this cosmic heavyweight remained invisible, its presence betrayed only by the frantic motion of galaxies that should have been drifting apart in the expanding universe but weren't. The first clues emerged in the 1970s when astronomers mapping galaxy flows noticed something bizarre. Thousands of galaxies, including our local group, were streaming toward the same patch of empty space in the constellation Centaurus. The sheer scale of this motion defied logic. Even the combined mass of every known galaxy in that direction couldn't account for the pull. Whatever was yanking the cosmic strings had to weigh at least 10,000 times more than the Milky Way. Yet when researchers pointed their telescopes there, they found nothing, just the murky veil of the zone of avoidance where our galaxy's own dust blocks the view like a cosmic blindfold. Then came the game changer. X-ray observations pierced the fog, revealing not just one unseen behemoth but an enormous knot of matter. The Norma cluster, surrounded by a sprawling supercluster dubbed Laniakea, Hawaiian for immeasurable heaven. This structure, 500 million light-years wide, might explain part of the Great Attractor's pull, but here's the catch: even Laniakea's gargantuan mass falls short. There's still an unaccounted-for force, something beyond our current maps, yanking galaxies toward a mystery we've only begun to glimpse. The theories spiral into the extraordinary. Maybe the Great Attractor is just the tip of the iceberg, a signpost pointing to an even larger structure, like the Shapley supercluster, 800 million light-years beyond it. Or perhaps it's evidence of exotic physics, a cosmic string left over from the Big Bang, or a gravitational echo from a neighboring universe pressing against our own. The most unsettling possibility, that we're seeing the fingerprints of a flaw in our understanding of gravity itself, a sign that Einstein's equations break down on scales larger than we've tested. What makes the Great Attractor so mesmerizing isn't just its power. It's the reminder that even as we map the cosmos, vast unknowns still lurk in the shadows. Every galaxy caught in its grip is like a leaf floating down a river, hinting at a current we can't yet see. And until we peer deeper behind the Milky Way's dusty curtain, the universe's strongest hand will keep tugging us toward the answer. Most stars flicker gently, their light dimmed in predictable rhythms by orbiting planets or natural stellar pulsations. But KIC 8462852, better known as Tabby Star, doesn't play by those rules. Nestled in the constellation Cygnus, this otherwise ordinary F-type star behaves like a cosmic light switch, dimming by up to 22% at irregular intervals, sometimes for days, other times for weeks. No known celestial phenomenon explains these erratic blackouts, and the more astronomers study it, the weirder it gets. The mystery began in 2015 when citizen scientists sifting through Kepler Space Telescope data flagged the star's bizarre light curve. Unlike the symmetrical dips caused by planets, Tabby Star's dimming was jagged, asymmetric, and wildly inconsistent. Even stranger, historical data revealed its overall brightness had dropped by 14% between 1890 and 1989. An impossible feat for a mature star like this. Stars don't just fade like aging light bulbs, at least not naturally. Cue the megastructure hypothesis. Astronomer Jason Wright famously suggested the dimming could stem from a colossal artificial construction, a Dyson swarm, a hypothetical energy harvesting array built by an advanced civilization. The math was tantalizing. To block that much light, the structure would need to be vastly larger than Jupiter. Enthusiasts scoured the star's radio emissions for signs of technology, while others speculated about massive solar panels or even a star-encircling supercomputer. But the truth, as always, proved more nuanced. Natural explanations abound, though none fit perfectly. One leading theory involves swarms of disintegrating comets, their dusty debris trailing across the star's face in irregular clumps. Another posits an immense ringed planet with chaotic, warped rings casting jagged shadows. There's even the possibility of an interstellar dust cloud, though such clouds typically scatter specific wavelengths of light, something Tabby Star doesn't consistently do. Then there's the star itself. Spectroscopic analysis revealed no excess infrared radiation, the telltale heat signature you'd expect from orbiting dust. This absence forced scientists back to the drawing board, considering wilder ideas like a recent planetary collision or even a rogue black hole's accretion disk passing in front of the star. What makes Tabby Star so compelling isn't just the lingering question of what's blocking its light, it's the way it forces us to rethink what's possible. Every anomalous flicker is a reminder that the universe doesn't owe us tidy explanations. Whether the answer lies in unknown astrophysics or, however unlikely, something beyond our current understanding, this star keeps us guessing. And in the grand search for cosmic truth, that's what makes it unforgettable. The moon shouldn't have secrets left. We've walked on it, sampled its rocks, mapped its craters. Yet one of its most baffling mysteries lies buried in ancient lunar rocks: magnetism. Today, the moon's magnetic field is practically non-existent, weaker than Earth's by a factor of 100,000. But samples brought back by Apollo astronauts tell a different story: traces of a magnetic field once as strong as Earth's, lasting for over 1 billion years. Here's the problem: magnetic fields require churning molten metal cores like Earth's dynamo. The moon's core too small and cold to generate that kind of power. So how did our closest cosmic neighbor pull off this impossible feat? The leading theory sounds like something from a cosmic demolition derby. 4.5 billion years ago, a Mars-sized object nicknamed Theia slammed into early Earth, vaporizing rock and flinging debris into orbit that eventually coalesced into the moon. Simulations show this collision could have superheated the moon's interior, creating temporary convection currents in molten metal, enough to jumpstart a magnetic dynamo. But there's a catch. Even the most optimistic models say this borrowed energy should have fizzled out after a few 100 million years. Yet lunar rocks reveal the field persisted 10 times longer, defying every known rule of planetary physics. Some scientists point to an even wilder solution: gravitational kneading. Early in its history, the moon orbited much closer to Earth, and our planet's immense tidal forces might have stretched and squeezed its interior like cosmic taffy, keeping the core molten far longer than expected. Others suggest a cascade of massive asteroid impacts reheating the moon's mantle, reigniting convection like stirring a cooling pot of soup. Then there's the radical idea that the moon's crust itself played a role: immense sheets of sinking molten rock generating electrical currents as they plunged toward the core, creating a magnetic field from the outside in. But the plot thickens. Recent studies of lunar rocks show the field didn't fade smoothly. It flickered, spiked, and even reversed polarity, like a cosmic light switch with a short circuit. This erratic behavior has no parallel on Earth or anywhere else in the solar system. Some researchers now suspect the moon's magnetism wasn't a single phenomenon but a series of desperate acts, each buying time against the inevitable freeze. What makes this anomaly so haunting isn't just the unsolved physics, it's the reminder that even familiar worlds guard cosmic riddles. The moon's magnetic ghost whispers that we've barely scratched the surface of how planets live, die, and defy expectations. And until we crack this case, every pale glow in the night sky carries a question. How much do we really know about the silent world above us? In 1954, newspapers roared with a startling headline: the U.S. Air Force had detected a mysterious object orbiting Earth, one nobody had put there. Dubbed the Black Knight satellite, this enigmatic presence would spiral into one of space's most enduring conspiracy theories. The lore paints it as an alien artifact, a 13,000-year-old sentinel watching us from the shadows. But strip away the myth, and you're left with a far stranger truth: a jumble of misidentified debris, Cold War paranoia, and human imagination run wild. The story's roots tangle back to radio pioneer Nikola Tesla, who in 1899 claimed to have intercepted strange, rhythmic signals he believed originated from beyond Earth. Decades later, in 1960, a U.S. Navy satellite named Grab detected unusual radio echoes, fueling speculation of a shadowy orbital presence. Then came the clincher. Grainy 1998 footage from the space shuttle Endeavour appeared to show a jagged, artificial object adrift near Earth, a clip that went viral as proof of the Black Knight. Here's where science steps in. What conspiracy theorists call an alien satellite is likely a quilt of unrelated phenomena stitched together by coincidence. Tesla's signals, almost certainly pulsars, neutron stars emitting regular radio bursts decades before their official discovery. the Grab satellite's echoes. Space debris or military hardware from an era when orbital launches were top secret. As for that infamous Endeavour footage, it matches perfectly with a thermal blanket lost during a previous shuttle mission. Its irregular shape easily mistaken for something sinister when glimpsed against the void. Yet the myth endures, and for good reason. The Black Knight taps into our deepest fascination with the idea that we're not alone, that somewhere overhead something watches. It's a Rorschach test for the space age, reflecting our fears of surveillance, our awe of the unknown, and our knack for turning cosmic noise into narrative. Whether space junk or legend, its real power lies in the questions it forces us to ask. If we found proof of alien technology tomorrow, would we recognize it? Or would it slip past us, just another piece of debris in the celestial junkyard? The Black Knight isn't just a satellite story, it's a mirror. And sometimes the most intriguing mysteries aren't what's out there, but what we insist on seeing. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something unprecedented. A strange, needle-shaped object hurtling through our solar system at nearly 200,000 miles per hour. Its speed and trajectory left no doubt this visitor came from another star. They named it Oumuamua, Hawaiian for scout or messenger. But as scientists scrambled to study it, this interstellar interloper revealed behaviors so bizarre they sparked a firestorm of debate that still rages today. First, there was its shape. Radar measurements suggested Oumuamua was at least 10 times longer than it was wide, a tumbling cosmic cigar roughly a quarter-mile long. No known asteroid or comet in our solar system has such extreme proportions. Then came the real shocker. As it raced away from the sun, instead of slowing down as expected, it sped up. This wasn't minor measurement noise. Oumuamua's acceleration defied the laws of gravity alone, behaving more like a spacecraft firing thrusters than a lifeless rock. Mainstream astronomers scrambled for natural explanations. One leading theory proposed Oumuamua was a hydrogen iceberg, a chunk of frozen molecular hydrogen slowly evaporating in sunlight, creating an invisible jet that nudged it forward. The problem: hydrogen ice is so fragile it shouldn't survive interstellar journeys. Another camp argued it was a fractal-like dust bunny of primordial debris, lightweight enough for solar radiation to push it. Yet neither theory fully explains the object's strange brightness variations or lack of a visible coma. The fuzzy halo comets typically exhibit when warmed by the sun. Enter Harvard astrophysicist Avi Loeb with a bombshell hypothesis. What if Oumuamua wasn't natural at all? His calculations showed the object's acceleration matched what you'd expect from a thin, sunlight-powered sail, exactly the kind of technology humans are developing for interstellar probes. The implication: we might have spotted debris from an alien civilization, perhaps a discarded solar sail adrift between the stars. Critics pounced. They argued Oumuamua's behavior, while unusual, could still fall within the realm of natural phenomena we simply haven't observed before. After all, this was humanity's first encounter with an interstellar object. Our sample size was one. But Loeb fired back. Shouldn't science pursue all possibilities, no matter how unsettling? The debate crystallized a deeper tension in astronomy. How do we balance skepticism with the courage to consider radical ideas? By the time Oumuamua vanished from telescope view in early 2018, it had already rewritten the textbooks. Subsequent discoveries of interstellar objects like Borisov, a far more conventional comet, only deepened the mystery. Why was Oumuamua so different? Was it a bizarre cosmic fluke or the first hint of something far more profound? Whether alien artifact or exotic natural relic, one thing's certain: the universe is stranger than we imagined. And next time an interstellar visitor comes calling, we'll be watching closely. Einstein called it spooky action at a distance, a phenomenon so unsettling that it made him question the very fabric of reality. Quantum entanglement, the bizarre connection between particles that defies all classical intuition, remains one of physics' greatest unsolved puzzles. Here's how it works. Take two particles born from the same quantum event, say, electrons with opposite spins, and separate them by light years. According to quantum mechanics, measuring one instantly determines the state of the other, no matter how far apart they are. No signal travels between them, no force connects them, yet somehow they know. This isn't just theory. Experiments have confirmed entanglement's reality with chilling precision. In 1982, physicist Elaine Aspect fired paired photons in opposite directions, measuring their polarizations at detectors over 30 feet apart. The results violated classical limits, proving the particles coordinated faster than light could cross the gap. Later tests closed every conceivable loophole separating particles by over 800 miles, even using distant quasars to randomize measurement settings. The outcome never changed. Entangled particles behave as a single entity, mocking the idea of locality, the rule that objects can't influence each other faster than light allows. Einstein hated this. Alongside colleagues Podolsky and Rosen, he argued quantum mechanics must be incomplete, that hidden variables lurked beneath the math. But Bell's theorem in 1964 shattered that hope, showing no hidden variable theory could replicate quantum predictions. The universe, it seems, genuinely allows this ghostly coordination. So what's really happening? One interpretation suggests all particles exist in a vast quantum field, their fates intertwined at a fundamental level. Others propose wilder ideas, like particles subtly communicating through extra dimensions, or the entire universe being a holographic projection where distance is an illusion. The most radical possibility, that measurement doesn't reveal a particle's state but creates it, retroactively rewriting its entangled partner's history across spacetime. Practical applications already exist. Quantum cryptography uses entanglement to create unbreakable codes. Any eavesdropping disrupts the delicate link, alerting users. Future quantum computers might leverage entangled qubits to solve problems no classical machine could crack. Yet the deeper mystery endures. Entanglement hints that reality isn't just stranger than we imagine, but stranger than we can imagine. Every experiment peels back another layer, revealing a cosmos where connection transcends space, time, and perhaps even logic itself. The Hubble tension isn't just a scientific disagreement, it's a cosmic crisis. For decades, astronomers have measured the universe's expansion rate, the so-called Hubble constant, expecting different methods to converge on the same number. Instead, they've landed in a glaring contradiction. On one side, we have the gold standard approach, tracking distant supernova and the cosmic microwave background, relics of the early universe. These measurements suggest an expansion rate of about 67 kilometers per second per megaparsec. On the other side, observations of pulsating stars called Cepheids and gravitational lensing events point to a faster expansion, 73 kilometers per second per megaparsec. That 6-unit gap might sound trivial, but in cosmology, it's a chasm. The discrepancy is now at a confidence level of 5 sigma. Statistical speak for almost certainly real. What makes this tension so explosive is what it implies. Our understanding of the universe might be fundamentally flawed. The cosmic microwave background measurements taken by the Planck satellite reflect the universe as it was 400,000 years after the Big Bang. The Cepheid method, by contrast, measures the modern cosmos. If these numbers disagree, it suggests something monumental changed in the intervening 13 billion years, something missing from our models. Theories attempting to bridge the gap range from the subtle to the revolutionary. Maybe dark energy isn't constant but evolves over time, subtly tweaking expansion rates. Or perhaps the universe isn't as uniform as we thought, with giant voids or invisible structures warping our local measurements, the wildest possibility. That we're seeing fingerprints of undiscovered particles or forces. A fifth fundamental interaction that alters gravity on cosmic scales. Some researchers even speculate about early dark energy, a burst of repulsive force in the universe's infancy that could have left an imprint on galaxy formation. Skeptics argue the tension could still stem from measurement errors. Cepheids, for instance, are tricky to calibrate. Their pulsation rates depend on complex physics, and dust in galaxies can obscure their light. Yet as instruments like the James Webb Space Telescope double-check distances with unprecedented precision, the gap stubbornly persists. The stakes couldn't be higher. If the Hubble tension holds, it could force a rewrite of the standard model of cosmology, the very framework we use to understand the universe's birth, evolution, and fate. Whether it's new physics or a cosmic blind spot, one thing's clear: the universe is expanding faster than our theories can keep up. We think we know what normal matter looks like: stars, planets, gas clouds, the stuff you and I are made of. But here's the cosmic kicker: when astronomers tally up all the visible matter in the universe, half of it is missing. Not dark matter, not exotic particles, but good old protons and neutrons, the baryons that should be lighting up our telescopes. This isn't some accounting error. The numbers are rock solid, based on measurements of the cosmic microwave background and the universe's initial elemental soup. We know exactly how much ordinary matter was forged in the Big Bang. Yet today, roughly 50% of it has vanished without a trace. Welcome to the missing baryon problem, one of cosmology's quietest yet most profound puzzles. So where does half a universe's worth of atoms go? The leading suspect sounds like something from a cosmic crime novel, the warm-hot intergalactic medium, or WIM. Picture this: a vast, invisible web of superheated gas filaments stretching between galaxies, so diffuse it's nearly transparent. These threads, leftovers from the universe's large-scale structure formation, could house the missing baryons in the form of ionized oxygen and other trace elements, glowing faintly in X-rays or ultraviolet. The challenge: this gas is absurdly hard to detect. At temperatures between 100,000 and 10 million degrees, it's too hot for optical telescopes but too cool to stand out in most X-ray surveys. It's like searching for a whisper in a hurricane. Evidence is trickling in. In 2017, astronomers using the European Space Agency's XMM-Newton telescope spotted fingerprints of the WIM absorption lines in the X-ray light from a distant quasar, betraying the presence of oxygen ions stretched along a galactic filament. Similar studies with Hubble's ultraviolet instruments have found traces of highly ionized neon and carbon in the voids between galaxies. But these detections are mere glimpses, accounting for maybe 10% of the missing matter at best. The rest could be hiding in even more elusive forms, perhaps as ultra-diffuse clouds or as turbulent plasma churned up by galactic winds. Then there's the wild card: cosmic recycling. Some theorists argue the missing baryons might be locked in a perpetual cycle, ejected by supernova or active galactic nuclei, only to be swept up later by new star-forming regions. Imagine a universe where matter is constantly on the move, like water evaporating from oceans only to fall elsewhere as rain. The problem: even this elaborate dance doesn't fully close the gap. The hunt now turns to next-generation tools. The upcoming Athena X-ray Observatory, set to launch in the 2030s, promises to map the WIM in unprecedented detail, while radio astronomers are developing ways to detect the faint distortion these gas filaments imprint on the cosmic microwave background. Every new instrument brings us closer to solving the case, but for now, the universe's ledger remains unsettlingly unbalanced. What makes this mystery so humbling isn't just the missing matter. It's the reminder that even the familiar building blocks of reality can slip through our fingers. Stars and galaxies might dominate the cosmic postcards, but the true story of matter is written in the spaces between, in the faint traces we're only beginning to read. Until we find those lost atoms, we're like librarians who have catalogued half the books, unaware the rest are written in invisible ink. deep in the constellation Boötes lies a cosmic horror story, not of monsters or black holes, but of absence itself. Stretching 330 million light-years across, the Boötes void is a spherical nightmare of nothingness, so vast it could swallow 60,000 Milky Ways without a trace. Astronomers call it the Great Void, and for good reason. Where most patches of space contain thousands of galaxies, this one holds maybe 60. That's like finding a single grain of sand in an Olympic-sized swimming pool. The first hint of this eerie emptiness came in 1981, when astronomer Robert Kirshner and his team noticed an unnatural gap in galaxy surveys. Follow-up observations revealed the truth. This wasn't just a quiet neighborhood, it was a ghost town on a cosmic scale. So how does a chunk of the universe end up so empty? One camp argues it's a statistical fluke, a supervoid where matter just happened to clump elsewhere, like a foam bubble in the cosmic latte. But even that explanation strains credulity. Simulations show voids this large should be vanishingly rare in our current models of galaxy formation. The alternative, we might be seeing the aftermath of something far stranger, an ancient collision between universes in the multiverse, leaving behind a scar of vacuum energy, or the remnants of a phase transition in the early cosmos where space itself briefly reset. Some theorists even speculate about primordial black holes devouring everything in the void's infancy, though no direct evidence supports this. The Boötes void also throws a wrench into our understanding of galaxy evolution. Normally, galaxies form where dark matter's gravity pulls gas into dense knots, but in the void, that process seems broken. The few galaxies that do exist here are oddballs, isolated, hydrogen-poor, and often weirdly shaped, as if struggling to survive in a cosmic desert. Some show ring structures, likely caused by gas being violently stripped away during encounters with other galaxies billions of years ago. These galactic castaways might be the last survivors of a time before the void took hold. Then there's the eerie possibility that the Boötes void isn't entirely empty, it's just hiding matter in forms we can't see. Some dark matter theories predict ultra-diffuse galaxies floating like invisible jellyfish, detectable only through gravitational lensing. Others suggest rogue planets or cold gas clouds too faint for current telescopes. The upcoming Vera Rubin Observatory could settle this by scanning the void for the faintest glimmers of starlight. What makes the Boötes void so unsettling isn't just its emptiness, it's the way it forces us to confront how little we understand about the universe's structure. Most cosmic maps focus on the glittering cities of galaxy clusters, but the voids between them might hold the real secrets, silent, sprawling, and waiting for us to listen. If the Boötes void is a cosmic ghost town, then the Eridanus supervoid is an even deeper cosmic enigma, a staggering billion light-year expanse of near-nothingness that might just hold the key to one of astronomy's coldest cases. Unlike the Boötes void's eerie emptiness, this region in the constellation Eridanus is infamous for something far more peculiar. A chilling anomaly in the cosmic microwave background, the afterglow of the Big Bang. Known as the CMB cold spot, this patch of sky is inexplicably colder than its surroundings by about 70 microkelvin, in a tiny number with universe-sized implications. The connection between the Eridanus supervoid and the cold spot is the kind of cosmic detective story that keeps physicists up at night. Here's the puzzle: voids, by their nature, are less dense than the rest of the universe, meaning light passing through them should lose a fraction of its energy, a phenomenon called the integrated Sachs-Wolf effect. In theory, this could explain the cold spot, but there's a catch. The supervoid's size and depth don't quite add up to account for the temperature drop. It's like finding a footprint too large for any known animal, hinting at something far stranger lurking beyond our current models. Skeptics argue it's all a cosmic coincidence, a random fluctuation in the CMB that happens to overlap with a large void. After all, the universe is vast and statistical flukes are inevitable. but the numbers are stubborn. The odds of such a cold spot appearing naturally are roughly 1 in 50. Not impossible, but uncomfortable enough to raise eyebrows. This tension has spawned wilder theories, from primordial textures, exotic defects in space-time left over from the Big Bang, to collisions with other universes in the multiverse. Some even suggest the cold spot is a bruise from a black hole in a neighboring universe bumping into ours during inflation. The plot thickens when you examine the supervoid itself. While most voids are roughly spherical, the Eridanus supervoid appears elongated, almost like a tunnel bored through the cosmos. Its galaxies are sparse, but not entirely absent, clustering in strange filaments that defy typical large-scale structure models. If this void formed naturally, it would require an unimaginable confluence of initial conditions, a perfect storm of cosmic rarity. What makes this anomaly so tantalizing isn't just the mystery, it's the way it forces us to question the limits of our cosmic maps. Are we seeing a statistical glitch or the first cracks in our understanding of the universe's infancy? The answer might lie in next-generation telescopes like the Simons Observatory, which will scrutinize the cold spot with unprecedented precision. Until then, the Eridanus supervoid remains a cosmic Rorschach test, one that challenges us to decide whether we're staring at a flaw in the data or a window into physics beyond our wildest dreams. Galaxies are supposed to play by certain rules. Dark matter is the invisible scaffolding that holds them together, the cosmic glue keeping stars from flying off into the void. But NGC 1052 didn't get the memo. This bizarre, ghostly galaxy, floating 59 million light-years away in the constellation Cetus, is the cosmic equivalent of a car driving without an engine. It shouldn't move, it shouldn't exist, and yet there it is, a shimmering enigma that's forcing scientists to rewrite the textbooks. Discovered in 2018 by a team led by astronomer Pieter van Dokkum, DF2 looks nothing like your typical spiral or elliptical galaxy. It's a ultra-diffuse galaxy, a wispy, translucent cloud of stars so sparse you could fly right through it without hitting anything. But here's the real shocker. When researchers measured the motion of its star clusters, they found almost no gravitational pull beyond what the visible stars themselves provided. No dark matter halo, no hidden mass, just a skeleton of stars drifting lazily through space, untethered from the invisible hand that rules every other galaxy we've ever seen. The implications are staggering. For decades, dark matter wasn't just a theory, it was the foundation of modern cosmology, the only way to explain why galaxies rotate the way they do, how they cluster, even how they formed in the first place. DF2 doesn't just challenge that model, it throws a wrench into it. If galaxies can exist without dark matter, then what is dark matter, and why does it seemingly abandon some galaxies while clinging desperately to others? Skeptics scrambled for explanations. Maybe DF2 had dark matter at some point, only to have it ripped away by a violent encounter with another galaxy. Yet there's no sign of such a collision, no tidal tails, no distortions, just a serene, undisturbed expanse. Others suggested DF2 might be a failed galaxy, one that formed in an unusually empty pocket of the cosmos where dark matter was scarce. But simulations show even those galaxies should accumulate some dark matter over time. Then came the real curveball. DF2 isn't alone. Its sibling, NGC 1052 DF4, also shows a startling lack of dark matter. Suddenly, what seemed like a fluke became a pattern, one that hints at an entirely unknown pathway for galaxy formation. Could these be the remnants of a shattered larger galaxy? Or the product of some exotic physics we haven't even dreamed of yet? What makes DF2 so revolutionary isn't just its defiance, it's the questions it forces us to ask. If dark matter isn't universal, then our cosmic maps are missing whole chapters. Maybe dark matter interacts with visible matter in ways we don't yet understand. Or perhaps, as some theorists now speculate, gravity itself behaves differently under certain conditions. bending the rules in places we've never thought to look. Every new observation of DF2 peels back another layer of mystery. The latest studies suggest its globular clusters, tight knots of ancient stars, are far larger and brighter than they should be, as if the galaxy itself is a cosmic Frankenstein's monster stitched together from mismatched parts. Yet it moves through space with eerie grace, a silent rebel in a universe that supposedly demands conformity. For now, DF2 stands as a cosmic paradox, a reminder that even our most cherished theories are provisional. The universe doesn't owe us tidy explanations, and sometimes the most profound discoveries come not from the places that follow the rules, but from the outliers that break them. Saturn's North Pole looks like something out of a cosmic geometry textbook, a perfect six-sided hurricane stretching 20,000 miles across, with winds screaming at over 300 miles per hour. This isn't a fleeting storm or an optical illusion. The Saturn hexagon is a persistent, razor-sharp structure that's been churning for at least 40 years, possibly centuries, defying every law of atmospheric physics we thought we understood. Unlike Earth's chaotic, ever-shifting weather systems, this is a planetary-scale precision machine, a whirlpool with edges so exact you could plot them with a protractor. So how does a gas giant cook up such an unnatural-looking storm? Fluid dynamics offers clues, but no complete answers. When NASA Voyager probes first spotted the hexagon in 1980, scientists scrambled to recreate it in labs. The leading theory involves something called Rossby waves, giant ripples in Saturn's jet streams that could, under just the right conditions, pinch the planet's polar winds into geometric shapes. Imagine stirring a cup of tea with a spoon, then watching the liquid form temporary honeycomb-like patterns as it slows. Now scale that up to a planetary atmosphere with no spoon, no cup, and no pause button. Here's the catch: Earth has Rossby waves too, yet our poles have never whipped up anything resembling a hexagon. The difference lies in Saturn's sheer ferocity. With no solid surface to break them, the planet's jet streams can reach speeds 10 times faster than Earth's mightiest hurricanes. Combine that with Saturn's deep atmosphere, a churning soup of hydrogen and helium, and you've got a recipe for stable, self-reinforcing turbulence. Some models suggest the hexagon is essentially a standing wave, a resonant vibration locked in place by Saturn's rotation, like a musical note held indefinitely in a feedback loop. Yet even these explanations struggle to account for the hexagon's eerie precision. Why 6 sides? Why not 8 or 5? Laboratory experiments show that spinning fluids can produce polygons, but they're usually transient, wobbling between shapes before dissolving. Saturn's hexagon, by contrast, is stubbornly stable, a freak of fluid mechanics that behaves more like a crystalline solid than a storm. Some researchers speculate the planet's internal heat plays a role fueling convection currents that sculpt the jet stream from below. Others wonder if Saturn's intricate ring system somehow casts gravitational shadows that shape polar weather in ways we can't yet model. The hexagon's most haunting feature might be its longevity. Observed continuously since the Voyager era, and likely existing long before, it's a clockwork tempest that outlasts every human-built instrument sent to study it. When the Cassini probe dove toward Saturn's poles in 2017, it captured the hexagon in stunning infrared, revealing layered hazes and swirling vortices at its edges, features that hint at deeper, hidden dynamics. What makes this anomaly so mesmerizing isn't just its defiance of Earth-bound meteorology, it's the reminder that nature's rulebook has chapters we've never opened. Gas giants might be cosmic laboratories for physics we can't yet replicate, where storms come with angles and weather runs on algorithms we're only beginning to decipher. Until we land a probe in that 6-sided maelstrom, Saturn's hexagon will remain both a masterpiece of fluid dynamics and a silent challenge. How much stranger could the universe's weather get? On New Zealand's North Island, nestled within the volcanic caldera of Mount Tarawera, lie two lakes so bizarrely colored they sparked an interstellar conspiracy. The larger Lake Tarawera gleams a deep sapphire blue, while its neighbor, Rotomahana's smaller basin, burns an almost neon shade of pinkish orange. Side by side, they look less like natural bodies of water and more like a cosmic artist's palette, a visual punchline so striking that mid-century UFO enthusiasts swore it was evidence of extraterrestrial terraforming. The truth, as it turns out, is both stranger and more beautiful than any alien myth. The lake's dramatic split personality comes down to a hidden alchemy of chemistry and geology. Lake Tarawera's classic azure hue is the result of pristine rainwater filtering through porous volcanic rock, emerging so pure it scatters sunlight in that iconic blue, the same optical trick that paints Earth's skies. But Rotomahana's fiery tones, that's where the real magic happens. Beneath its surface, hydrothermal vents pump a cocktail of dissolved minerals into the water: iron oxides, antimony sulfides, and microscopic particles of colloidal silica, creating a natural dye so concentrated it shifts with the angle of the sun. At midday, the lake can appear gold-tinged. By dusk, it deepens to a molten copper. The kicker, Rotomahana's current incarnation didn't even exist before 1886. That year, Tarawera's cataclysmic eruption, New Zealand's deadliest in recorded history, vaporized the original Lake Rotomahana, along with its famed pink and white terraces, silica formations once called the eighth wonder of the world. When the lake reformed decades later, it did so atop a geothermal battlefield, its waters infused with minerals from the very explosions that birthed it. Modern scientists have clocked Rotomahana's temperatures at a bathtub-warm 120 degrees Fahrenheit near vents, with acidity levels hovering around pH 3, comparable to grapefruit juice. This extreme environment breeds extremophiles, heat-loving microbes that tint the water with carotenoid pigments, the same molecules that color carrots and flamingos. It's a living, breathing chemical reaction, one that transforms what could have been a simple volcanic lake into a shimmering alien-looking spectacle. What makes these lakes more than just a pretty oddity is the way they mirror the universe's knack for turning destruction into artistry. A volcano annihilates a natural wonder only to replace it with something equally breathtaking. Aliens need not apply. The cosmos cooks up plenty of marvels on its own. And sometimes the most otherworldly sights are the ones born right beneath our feet. The thin, rust-colored air of Mars holds a secret that's been taunting scientists for decades: fleeting whispers of methane, a gas that shouldn't vanish as quickly as it appears. On Earth, methane is often a calling card of life, belched by microbes and livestock. But on Mars, its sporadic presence is a riddle wrapped in layers of contradiction. One day, NASA Curiosity rover detects a tenfold spike in methane levels near Gale Crater. The next, orbiters like ESA's Trace Gas Orbiter scan the same area and find nothing. This isn't just a measurement error, it's a cosmic shell game, and the stakes couldn't be higher. If Mars is producing methane, we need to know whether it's coming from geology or something far more intriguing. What makes methane so compelling is its stubborn refusal to stick around. Sunlight and chemical reactions should break it apart within a few hundred years, yet Curiosity's data shows levels fluctuating wildly over mere days. Imagine lighting a candle in a windstorm only to find it flickering back to life unpredictably. Possible explanations split into two camps, each with earth-shaking implications. The biological camp points to subterranean microbes, perhaps clinging to life in briny aquifers below the permafrost, exhaling methane as they metabolize. It's not as far-fetched as it sounds. Earth's toughest extremophiles thrive in similar conditions, from Antarctic ice to acidic volcanic springs. The geological alternatives are no less dramatic. Serpentinization, a process where water interacts with olivine-rich rocks, could generate methane without life. Mars's volcanic past might have left pockets of heat that still cook gas today. Or buried clathrates, icy cages trapping ancient methane, could be cracking open under pressure shifts. But here's the hitch: none of these fully explain the gas's erratic behavior. If geology were the culprit, we'd expect steady seeps, not vanishing acts. Curiosity's readings add another twist. The rover's onboard lab, SAM, found methane levels often spike at night and dip by day, almost as if the gas is being absorbed by the soil when the sun rises. Some scientists speculate the Martian surface acts like a sponge, soaking up methane when salts like perchlorates activate in sunlight. Others propose atmospheric dynamics, where methane gets trapped near the ground at night and diluted by daytime winds. The most tantalizing clue: seasonal patterns. Over 5 Mars years, Curiosity noticed methane peaking in late summer, a rhythm that hints at temperature-driven processes like thawing subsurface ice releasing trapped gas. But even this fails to solve the puzzle entirely, as the trace gas orbiter, designed specifically to sniff methane from above, has largely drawn blanks. The discrepancy might come down to timing. If methane escapes in brief, localized plumes, orbiters could easily miss it while rovers catch the tail end. This isn't just academic nitpicking. If the methane is biological, it would redefine our place in the cosmos, proving life isn't Earth's monopoly. If geological, Mars might still hide active processes that reshape our understanding of rocky planets. Future missions like NASA Mars Life Explorer aim to analyze carbon isotopes in the methane, a fingerprint that could reveal its origin. Life tends to prefer lighter carbon-12, while abiotic processes often leave heavier carbon-13 behind. Until then, Mars keeps its secrets close. Every new data point deepens the mystery, reminding us that the red planet's quiet surface might be hiding whispers of something extraordinary, whether ancient, alive, or something we haven't even imagined yet. Venus has always been the solar system's cautionary tale, a hellscape of crushing pressures, acid clouds, and temperatures hot enough to melt lead. But in 2020, astronomers dropped a bombshell that made us rethink everything we knew about our twisted sister planet. The discovery: phosphine gas, a molecule so intrinsically linked to life on Earth that its presence in Venus's atmosphere sparked immediate frenzy. Here's why this was monumental: phosphine shouldn't exist there. On our planet, this stinky, flammable gas is almost exclusively produced by anaerobic bacteria, thriving in oxygen-free environments like swamps or human guts. Yet spectroscopic observations from the James Clerk Maxwell Telescope and the Atacama Large Millimeter Array revealed a faint but unmistakable phosphine signature 50 kilometers above Venus's surface, precisely where temperatures and pressures are almost hospitable. The initial paper, published in Nature Astronomy, was cautious but electrifying. The team, led by Jane Greaves at Cardiff University, had spent years ruling out false positives. Volcanic activity: Venus has some, but not enough to explain the readings. Meteorite dust: not in those quantities. Photochemical reactions: the numbers didn't add up. The implication was startling. Either Venus harbored a previously unknown abiotic chemical pathway, or something was alive in those sulfuric acid clouds. The scientific backlash was swift and brutal. Critics pounced on the data, arguing the signal could be noise misinterpreted, a rogue spectral line from sulfur dioxide, a gas Venus's atmosphere has in spades. Others recalculated the phosphine abundance, claiming the original team overestimated it by orders of magnitude. By 2021, the debate had devolved into a tug-of-war between reprocessed datasets and bruised egos. Even the European Space Agency's Venus Express, which had orbited the planet for 8 years, found no trace of phosphine in its archival data. But here's where it gets messy. The initial detection wasn't easily dismissed. Independent teams using different analytical methods did confirm phosphine, just at lower levels. The controversy revealed a deeper issue. Venus's atmosphere is a chemical funhouse with reactions we barely understand. Some lab experiments now suggest phosphine could form when sulfuric acid droplets erode certain minerals in the clouds, releasing phosphorus atoms that then bond with hydrogen. It's a long shot, but so is extraterrestrial life. The most tantalizing twist: Venus's cloud decks have a habitable zone. Between 48 and 60 kilometers up, pressures and temperatures eerily mirror Earth's surface, just with a side of battery acid rain. Microbes on Earth, like Acidotheobacillus, thrive in similar conditions. Could floating, acid-resistant organisms be churning out phosphine as a byproduct? It's not impossible, just extraordinarily inconvenient to prove. Future missions might settle the debate. NASA Da Vinci Plus and Veritas, along with ESA's Envision, will scrutinize Venus's atmosphere with precision far beyond Earth-based telescopes. But for now, the phosphine debate lingers like the planet's own opaque clouds, a tantalizing enigma that forces us to confront how little we know about the boundaries of life. Whether the answer is chemistry or biology, one thing's clear: Venus just became the solar system's most unexpected wildcard. One of the solar system's most baffling boundaries isn't a planet or a moon, it's an invisible line in the cosmic sand, a frontier where the Kuiper Belt's bustling menagerie of icy objects suddenly vanishes. Picture this: out beyond Neptune, stretching from 30 to 50 astronomical units, lies a donut-shaped realm of frozen leftovers from the solar system's birth: comets, dwarf planets, and primordial rubble like Pluto and Arrokoth. But at roughly 50, the party abruptly ends. The number of Kuiper Belt objects doesn't taper off gradually, it plunges off a cliff, dropping by a factor of 10 in a cosmic heartbeat. Astronomers call this the Kuiper Cliff, and its existence defies every model of how planetary systems form. So what's slicing the outer solar system in half? The leading suspect sounds like a sci-fi plot twist: an unseen super-Earth lurking in the darkness. Dubbed Planet 9, this hypothetical world, estimated to be 5 to 10 times Earth's mass, could have carved the cliff's edge with its gravitational boot. Simulations show a distant, eccentric planet could herd smaller objects into tight orbital clusters while flinging others into the abyss, leaving behind the stark drop-off we see today. The math is seductive. Planet 9's predicted orbit aligns eerily with the strange trajectories of extreme trans-Neptunian objects like Sedna and Biden, which loop the Sun at bizarre, tilted angles. If real, it would rewrite the solar system's map, adding a ghostly giant we've somehow missed for centuries. But not everyone's convinced. Alternative explanations point to the solar system's chaotic infancy. During the gas giant's migratory dance 4 billion years ago, Jupiter might have rampaged inward while Neptune bullied its way outward, scattering the primordial Kuiper Belt like a cue ball breaking a rack. Some objects could have been ejected entirely, while others were packed into a narrow zone before Neptune's gravity slammed the door. There's even a wild card. What if the Sun stole a horde of icy bodies from a passing star during its birth cluster days? That could explain why the outer belt looks ransacked, because cosmically speaking it was. Yet the cliff's razor-sharp edge still nags at astronomers. Natural processes tend to be messy, leaving gradients rather than hard stops. The abruptness suggests something is actively maintaining this boundary, whether a hidden planet, a resonance trap, or forces we haven't yet imagined. New Horizons, the probe that gave us our first close-up of Pluto, is now venturing beyond 50O, scanning for clues. Every icy pebble it detects, or doesn't, could tip the scales toward one theory or another. What makes the Kuiper Cliff so haunting isn't just the mystery, it's the reminder that our solar system's story is still being written. Whether the culprit is Planet 9, ancient chaos, or something stranger, one thing's clear: the frozen fringe of our cosmic neighborhood holds secrets that could rewrite everything we thought we knew about home. The cosmic microwave background, the faint afterglow of the Big Bang, should be the universe's most democratic feature, a perfectly even tapestry of ancient light stretched across the sky. But in 2005, astronomers staring at data from the Wilkinson microwave anisotropy probe noticed something that made their blood run cold. The hot and cold spots in this primordial radiation weren't randomly scattered as expected. Instead, they seemed to align along a bizarrely specific axis, as if the universe itself had a North Star. Dubbed the axis of evil by a shuddering scientist, this eerie pattern defies the very foundation of modern cosmology, the cosmological principle, which states that the universe should look the same in all directions with no special vantage points. At the heart of the controversy is a number so improbable it feels like a cosmic joke. The chance of this alignment occurring randomly, less than 1 in 10,000. The axis points suspiciously toward the ecliptic plane of our solar system, raising the chilling possibility that it's not a feature of the universe at all, but some grotesque artifact of our own measurements. Yet after years of reanalysis, including data from the Planck satellite, the anomaly refused to vanish. If it's real, the implications are earth-shaking. It could mean the universe has a preferred direction, that our corner of space-time is fundamentally different from others, or worse, that we're seeing the fingerprints of a pre-Big Bang structure, a cosmic scar from something beyond our observable horizon. Skeptics have scrambled for explanations. Maybe it's residual contamination from our galaxy's dust, though meticulous filtering rules out most interference. Others suggest systematic errors in how we model the CMB, but no one's found a smoking gun. The most radical theories that the universe is finite and oddly shaped, like a hall of mirrors warping light on colossal scales. Or that we're seeing the gravitational tug of a parallel universe brushing against ours, a multiversal collision frozen in the afterglow of creation. What makes the axis of evil so unnerving isn't just its existence, it's the philosophical vertigo it induces. For centuries, we've clung to the idea that we're not special, that Earth is a speck in an indifferent cosmos. Now, we're forced to confront the possibility that the universe might, after all, have a front row and a back, and we're staring straight down the center aisle. Until we crack this code, the CMB remains both our oldest relic and our greatest riddle, whispering that the universe is far stranger, far less random than we ever dreamed. If black holes are the universe's ultimate cosmic vacuum cleaners, sucking in everything that crosses their event horizons, then white holes are their theoretical opposites, cosmic fire hydrants spewing out matter and energy with relentless force. These hypothetical objects, first proposed as mathematical curiosities in Einstein's theory of general relativity, are essentially black holes running backward in time. Where a black hole's gravity is so strong that nothing escapes, not even light, a white hole would repel all matter, forbidding anything from entering. Picture a one-way door where the "Do Not Enter" sign is written in the fabric of spacetime itself. General relativity treats time as symmetrical, meaning that for every solution describing a black hole, there's a corresponding solution for a white hole. They're two sides of the same coin, linked through the equations like shadow and light. Some theories even suggest that a black hole, when it reaches the end of its life, could theoretically transform into a white hole, vomiting back out all the material it ever consumed. Yet despite decades of searching, no white hole has ever been detected, leaving scientists to wonder if they're purely mathematical artifacts or if the universe simply forbids their existence. One reason for their absence might be thermodynamics. Black holes obey the second law, increasing entropy as they devour matter. But a white hole ejecting energy in a perfectly ordered stream would seem to violate this fundamental rule, effectively reversing the arrow of entropy. Another problem is stability. White holes are thought to be incredibly fragile. If even a single particle of matter were to breach their event horizon, the entire structure would theoretically collapse into a black hole, meaning any naturally occurring white hole would likely self-destruct almost immediately. Yet the hunt hasn't been abandoned entirely. Some astrophysicists speculate that certain bizarre cosmic phenomena, like gamma-ray bursts or fast radio bursts, could be signatures of white holes briefly flickering into existence before vanishing. Others propose that white holes might be hiding in plain sight, perhaps as the hypothetical other end of a wormhole, offering a pathway between distant regions of spacetime. And in the realm of quantum gravity, where relativity and quantum mechanics collide, white holes might emerge as part of a deeper understanding of how information escapes a dying black hole. Whether real or just a beautiful quirk of mathematics, white holes force us to stretch our imaginations. They challenge our assumptions about time, causality, and the very nature of reality. If they do exist, they might rewrite the rules of the cosmos. If they don't, they still remind us that the universe is far stranger and more inventive than we can yet comprehend. The search continues, not just for white holes, but for the deeper truths they might reveal. The Fermi Paradox taunts us with silence, billions of planets ripe for life, yet no signs of neighbors. But what if the reason we haven't found aliens isn't because they don't exist, but because they're hiding? Enter the dark forest hypothesis, a chilling answer ripped straight from cosmic survival tactics. Picture the universe as a vast, pitch-black woodland where every civilization is a hunter tiptoeing through the trees, terrified of giving away their position. The logic is brutal. Any species advanced enough to broadcast its location risks attracting something far worse: predators, berserker probes, or rival empires hellbent on extermination. In this scenario, silence isn't just golden, it's the difference between thriving and extinction. This isn't just sci-fi paranoia, the math is unsettling. Given the age of the universe, any civilization with even a modest head start could have colonized the galaxy millions of times over. That they haven't suggests something, or someone is culling the herd. Historians point to Earth's own tragic examples: indigenous cultures decimated by technologically superior invaders. Scale that up to cosmic proportions, and the dark forest starts to feel less like fiction and more like a grim inevitability. Then there's the inverse possibility, not that aliens are hiding from us, but that we're beneath their notice. Imagine an ant hill at the base of a skyscraper. The humans inside might be real, but they're too preoccupied with their own world to register the ant's existence. This zoo hypothesis suggests advanced civilizations observe us passively, adhering to some galactic prime directive. But there's a darker twist, the lab hypothesis, where Earth is a controlled experiment, and any attempt to escape our planetary petri dish triggers quarantine or termination. Other solutions border on the existential. The Eastivation hypothesis proposes that advanced species aren't hiding or ignoring us, they're sleeping. In a universe where usable energy becomes scarce, hyper-intelligent civilizations might enter long-term hibernation, waiting for the cosmos to cool enough to maximize computational efficiency. To them, we're not even worth waking up for. Perhaps the most humbling answer is the transcension hypothesis, that civilizations don't die out but evolve beyond physical forms, uploading their consciousness into black holes, scale quantum computers, or higher dimensions. In this view, the reason we don't see aliens is because they've graduated to realities we can't yet perceive, leaving behind the crude, material universe like children outgrowing toys. Each theory forces us to confront uncomfortable truths about intelligence, survival, and our place in the cosmic pecking order. Whether the universe is a battlefield, a classroom, or a graveyard, one thing's clear: the silence isn't empty. It's listening. The axis of evil doesn't just defy expectations, it shreds them, leaving cosmologists scrambling for explanations beyond the standard playbook. While mainstream theories wrestle with measurement errors or galactic interference, the anomaly's stubborn persistence has given rise to fringe ideas so radical they flirt with rewriting physics itself. One of the most mind-bending contenders, the idea that the universe might be rotating. Picture the cosmos as a spinning top, its grand motion imprinting a preferred direction on the cosmic microwave background. This isn't just poetic imagery. General relativity technically allows for universal rotation, though it would require a primordial twist baked into space-time at the Big Bang. If true, the axis of evil could be the ghost of that initial spin, a cosmic gyroscope still tracing its arc across the sky. Then there's the even wilder notion that the alignment isn't a flaw in our models but a relic from before the Big Bang. Loop quantum gravity, a leading theory of quantum spacetime, suggests our universe might have rebounded from a previous collapsing phase, a big bounce. In this scenario, the axis could be a scar from that pre-collapse universe, a structure so vast it survived the reset. Imagine pressing two sheets of paper together. The creases from the first might faintly transfer to the second. Similarly, the CMB's odd alignment might be an echo of an earlier cosmos, its geometry whispering through the birth of our own. Some theorists go further, proposing that the axis marks where our universe brushed against another in the multiverse. Brain cosmology, inspired by string theory, suggests we inhabit a three-dimensional brain floating in a higher dimensional space. Collisions with neighboring brains could have left gravitational bruises, signatures now frozen in the CMB's patterns. It's a cosmic version of pressing your hand against a foggy window. The imprint lingers long after the touch, but perhaps the most unsettling possibility is that the axis is evidence of a simulation. Just as a rendered video game might cut corners by repeating textures to save processing power, the universe's apparent symmetry break could hint at underlying computational shortcuts. The alignment would then be a glitch in the cosmic code, a place where the simulation's architecture bleeds through. Each theory, no matter how speculative, forces us to confront the same unnerving truth. The axis of evil might not be an error to correct but a clue to something far grander. Whether it's a spinning universe, a multiversal fingerprint, or something beyond our current math, the anomaly refuses to be ignored, and until we crack its code, it stands as both a taunt and an invitation to look deeper, think wilder, and question everything we thought we knew about the fabric of reality. Oumuamua didn't just pass through our solar system, it ripped open a new chapter. Astronomy. Before this cosmic interloper arrived in 2017, interstellar objects were considered hypothetical curiosities, the stuff of textbooks and simulations. But when that tumbling, cigar-shaped visitor screamed past the sun at nearly 200,000 miles per hour, it forced every telescope on Earth and beyond to snap to attention. Now, as more interstellar travelers like Borisov enter our neighborhood, scientists are scrambling to rewrite the playbook on how to study these messengers from the stars. The stakes couldn't be higher. Interstellar objects are time capsules from alien solar systems, carrying pristine clues about how planets form around other stars. But catching them is a cosmic game of speed chess. Unlike comets or asteroids from our own system, these visitors barrel through at extreme velocities, often giving us mere weeks or days to observe them before they vanish forever. Oumuamua's greatest lesson: we need to be ready. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time are now training their sights on the skies, armed with algorithms designed to flag interstellar interlopers the moment they cross into view. Unlike the delayed detection of Oumuamua, which was spotted on its way out of the solar system, next-generation surveys aim to catch these objects on their approach, buying precious time to dispatch probes. Enter the concept of interstellar interceptors. Space agencies are already designing missions that could lie in wait at strategic orbits, poised to rocket toward the next Oumuamua at a moment's notice. The European Space Agency's Comet Interceptor mission, set to launch in 2029, is a trailblazer, a parked spacecraft designed to race toward an incoming object within months of detection. But the real dream, a dedicated observatory like the Lyra project, which proposes using nuclear propulsion to chase down future visitors at speeds exceeding 100,000 miles per hour. What makes Oumuamua's legacy so transformative isn't just the technology, it's the paradigm shift. Before 2017, planetary science was a local affair focused on our solar system's own debris. Now we're forced to think galactically. The discovery that interstellar objects might be far more common than once thought, perhaps as frequent as one passing inside Earth's orbit every year, has upended old assumptions. Some researchers even speculate that objects like Oumuamua could be delivery vehicles for panspermia, ferrying life's building blocks between star systems. Then there's the wild card. What if the next visitor isn't natural? Oumuamua's controversial acceleration, still unexplained by mainstream science, has left a door cracked open for extraordinary possibilities. Future objects exhibiting similar anomalies might warrant dedicated SETI monitoring, scanning for radio signatures or other technosignatures. The Galileo project, led by Avi Loeb, is already designing instruments to hunt for potential artificial interstellar objects, blurring the line between astronomy and the search for extraterrestrial intelligence. But perhaps the most profound change is cultural. Oumuamua shattered the illusion that our solar system is an island, isolated from the broader galaxy. Its very existence whispers that the cosmos is dynamic, interconnected, and far more unpredictable than we imagined. Every pebble drifting between stars carries a story of distant supernova, violent planetary migrations, or even the stirrings of alien industry. The next time one arrives, we'll be watching, not as passive observers, but as interstellar archivists ready to decode the secrets of the void. From the Wow signal's cryptic 72-second scream to the Great Attractor's invisible tug, from dark matter's ghostly grip to the Oumuamua cliff's razor-sharp edge, these 25 anomalies aren't just cosmic oddities. They're cracks in the foundation of reality itself, each one a reminder that the universe operates on rules we've only begun to decode. Think of them as 25 puzzle pieces scattered across the cosmos, some whispering hints of alien intelligence, others screaming about gaps in our understanding of gravity, time, and the very fabric of space. They challenge us to question everything from the nature of matter to the boundaries of life. Take the Hubble tension, a numbers game that could rewrite cosmology, or Tabby Star, flickering like a malfunctioning streetlight in a neighborhood we thought we knew. Consider Oumuamua's impossible acceleration, the Martian methane's vanishing act, or Saturn's hexagon, a storm so precise it feels engineered. Even the Moon, our closest celestial companion, defies logic with its ancient magnetic field, a relic of forces we can't yet explain. And lurking behind it all, the axis of evil, a cosmic North Star we were never supposed to find, hinting that the universe might have a preferred direction after all. What binds these mysteries together isn't just their strangeness, it's their refusal to fit neatly into textbooks. They're not problems to be solved with a tweak of existing theories, but invitations to tear down old frameworks and imagine new ones. The universe, it seems, is less a clockwork mechanism and more a living, breathing enigma, one that delights in upending our assumptions. But here's the thrilling part: we're on the brink of answers. The James Webb Space Telescope peers deeper into the infrared than ever before, hunting for the faint glow of the first galaxies or the chemical fingerprints of distant atmospheres. LISA, the upcoming gravitational wave observatory, will listen for ripples in spacetime from collisions we can't yet fathom, perhaps uncovering hidden dimensions or exotic matter. Missions like Europa Clipper and Dragonfly will probe icy moons for life's building blocks, while next-generation radio telescopes scan the skies for signals that might finally resolve the Fermi Paradox. The greatest lesson these anomalies teach us: curiosity is our compass. Every unanswered question, every paradox is a beacon guiding us toward deeper truths. So stay hungry, stay skeptical, and most of all, stay wonderstruck, because the cosmos still has stories left to tell, and the next chapter might be stranger than anything we've dared to dream.